Hi everybody. In this video, we will try to learn how to use polar coordinates to calculate double integration through an exercise. The exercise saying that there is a circle of radius A and it is shown here. You can see the circle is not centered at the origin. It is shifted to the right. The circle has radius A, and it's clear that the center is located at x equal A and y is equal to 0. So let's start asking a few questions and answering them in clear way. We're going to start with part A of the exercise, saying that find out the equation of the circle in polar coordinates. So we're going to find the equation of a circle, but we're going to use polar coordinates to do that. Now the way to do it is, first we know the equation of a circle using Cartesian coordinates, which is x minus the center, the x coordinate of the center, square, plus y minus the center, the y coordinate, which is 0, square. So that's the general equation of a circle, and that should equal the radius square. Now that's the equation of a circle using Cartesian coordinates. To write it in polar coordinates is easy. It's just we have to substitute x and y for their values in polar coordinates. We already know that x is equal to r, the radius r, times cosine theta, and y is equal to r sine theta. Before we do that, remember that this circle is shifted to the right, and that means the values of x are all positive. So x is positive. We can add this information here, that x could be or should be more than, or it could be equal to 0. Now what that means is the following: because x is always greater than or equal to 0, and we already know that r is always positive or it could be 0, so that constraint means that cosine theta has to be positive, and that means theta has to be in the first and fourth quadrant. Of course, this is clear from the graph. So theta will be in the first quadrant or the fourth quadrant, and the values for theta should be between negative pi over 2 to pi over 2. So that's a good thing to remember from the start. So these are the values of theta. Now we just go and substitute the values of x and y in the equation, and we just simplify it to find the equation of the circle. We're going to substitute. So x is r cosine theta minus a square plus y, which is r sine theta minus 0, and that's square, and that should equal to a square. Now with little mathematics, you can simplify this equation, and I will leave one step for you to prove that. What you will end up with the following equation: r square minus 2a r cosine theta, and that should equal to 0. So the above equation will simplify to this. Now still we did not finish, because this also could be simplified. Now we're going to take r common factor. So r times, open bracket, r minus 2a cosine theta, this should equal to 0. Now from here we have to conclude the equation of the circle. Of course, at the beginning you would say there are two solutions to this equation. So either r is equal to 0. However, r equals 0, even though it satisfies this equation, it's not the solution of a circle, because r equals 0, as you can see, it's only at one location. This is true. At other values, r is not 0. So the solution to this equation is not this. It's in fact the bracket is equal to 0, and from that we conclude that r should be equal to 2a multiplied by cosine theta, and that is the equation of the circle in polar coordinates. Let's check. Let's take a few values for theta and check the values of r. Let's start with theta equals 0. Now theta equals 0 means we are on the positive x-axis. Now if you put theta equals 0, cosine 0 is 1 and r is 2a. So now you can see that when theta equal to 0, so that's the first value we got, r is equal to 2a. So that's the value of r. I can write it, draw it like this. That's r equal to a. Let's take another value for theta. So for example, let's take another value for this theta, and let's find what is this value of r. Now this will be the value of r. So I just need to know what theta should I substitute. You can take any value for theta and you will find the answer. For example, let's try theta to be 45 degrees. So cosine 45 degrees will be 1 over square root of 2, and that will give you the value of r. Now theta is going to change up to pi over 2. So as we explained, theta, the values of theta are between negative pi over 2 to pi over 2. Notice that when theta is pi over 2, cosine pi over 2 is 0, and we get r equal to 0. Now that's easy. So what's happening is, as you increase this angle theta to larger values, you can see that the maximum value for theta will be pi over 2, and that will bring r to be 0. Same thing from the negative side of thetas. From theta negative pi over 2, same thing, it will be, r will be 0. So the values of theta are between negative pi over 2 to pi over 2, and this is the equation of the circle using polar coordinates, and you can see that r is a function of theta. R changes in value. It depends on the value of theta. If we change theta, you will get a different value for r. So that is part A. Let's go to another part. Let's say part B. Now let's go back to that circle, same circle, and find the area of that circle. Now, whenever we are dealing with circles or part of circles, I would always think about polar coordinates, about using polar coordinates to calculate quantities like area. So I'm gonna solve for area using polar coordinates and using double integration. Remember that area is defined to be the enclosed area of dx dy, and the boundary is the circle, because we are looking at the area inside that circle. So we not need to just to look at the region, that's the circle, and try to calculate this integration. But that's in Cartesian coordinates, and it's not going to be easy, even though we can try it and do it. However, I'm going to use polar coordinates to do this. So let's see how to use polar coordinates to calculate areas. So let's go back to the circle. This is our circle. And let's draw one value for r. R will start from 0, and let's change r until we hit the curve, that's the circle. Now notice that this line we draw has the same value for theta. Theta is constant on this line. Only r is changing. And you can see r is changing from the smallest value, which is 0, and it will go up to the maximum value, which is when it hits the circle, the boundary of the circle. Now this r, or this line, has the equation of theta is constant. For example, this could be theta equal 30 degrees. Now let's choose a slightly different theta. Let's increase theta little and draw another line. Let's choose a different color. Now this is a second line which has the equation theta is constant, but it's a little bit different from the theta of the previous line. Now those two lines have a small angle between. Now let's consider this small angle to be very, very small, infinitesimally small, and let's call it d theta. So let's call this angle d theta. That's the small angle between the two lines. Even though it's very small, infinitesimal, I draw it big just to see and to look at the picture clearly. So now the two lines, they have, each one of them has constant theta. Now in this way, we got a slab of this region. Now we're gonna cut this slab into smaller pieces. And now the pieces are, I'm gonna draw now a constant r. I'm gonna draw a curve with constant r, but theta is changing. Now constant r means a circle around the origin. So let's draw a part of a circle. So that's a circle, or a part of a circle. Now this circle, or this part of a circle, has the equation r is constant. R doesn't change. What is changing is theta, is the angle. Now let's choose another value for r, which is also will be constant, and then we will get this arc also. Now what I am interested in is this small area in between that's enclosed inside. This small area here. Notice that this small area is enclosed by 4 curves. 2 of them are theta is constant. So this one has the equation theta is, let's say, theta 1 equal theta 1. This one has a theta that's slightly more than the previous one. Now those two lines, they correspond to, one of them is r equals something, some number, constant, and the other one has a slightly larger r by a small difference. Now the question is, what is this area that we draw in this picture? Can we find the value of this area? And let's call this area dA. It's a very small area. Now the value of this area is, it's almost, because it's so infinitesimal, it looks like a square or a rectangle. The sides are, look at this side now. This one is the arc, is an arc which is opposite to the angle d theta. This is r times d theta. So that's the arc, the length of this little arc. Now the width of that region is just dr. So this one is just dr. So now the area enclosed, you can say it is just r d theta, that's the arc length, times dr. And that will give us the small element of area in polar coordinates. So to find the total area now, I'm going to divide the whole circle into similar pieces, areas, and then I'm going to add all these small areas to find the total area. And I'm going to write it like this. The total area will be the double integration of r d theta dr. The only problem left is to determine what are the limits that we should put in these integrations. If you understand this part so far, let's move to the next part, and that's to determine the limits. Now it depends on which order we want to do. Do we want to start with integration over theta and then finish with r, or the opposite? Now in general you can do any order you want. However, sometimes one order is easier than the other. So it depends on the problem. And for this problem, probably I would choose dr. And I will leave it to you to change the order and to try to find it in a different order. So let's find the area. So I'm not going to start with d theta. I'm going to leave it alone. And I'm going to do the integration over r. So I got r dr now. And I just have to find the limits for r. And then once I do this, I'm going to go and find the limits for theta. Now, how do I find the limits for r? Well, it's not difficult too. So let's draw one line. And you can see that we always going to start from the origin, and then when we go up until we hit the circle, the curve of the circle. If you choose another r, again, you can see it will start from the origin, and then it will continue until it hits the circle. And you can choose another one. Again, you're going to see it will continue until it hits the circle. So as you can see, r will always starting from the smallest possible value, and that's r equals 0, and it will finish at the boundary of the circle. But we already in part A, we calculated what is that equation of the circle, and that r, that's the boundary of the circle, satisfies this equation. Is 2a cosine theta. So r will finish up with these values of 2a times cosine theta. These are the boundaries for r. Once we finish with r, we're going to now do the integration over theta. And that will be just by sweeping over the whole region. And you can see that we're going to start from the smallest value of theta, and then we're going to go up to the largest value of theta. And that's from theta equal negative pi over 2 until we reach pi over 2. These are the limits of the integration. Now we can do the calculations. The calculations are not difficult, they are easy. So let's do that. Of course, we're going to keep the integration over theta till the end. So that's from minus pi over 2 to pi over 2. I'm going to do the integration over r, which is easy. It will be r squared over 2. Now substituting the limits, so I'm going to get 2a cosine theta, and this will be squared divided by 2. So I'm left with this integration, which is equal to, now I have some constants I can take out. So I got 2a squared divided by 2. That's going to be out of the integration. And what is left inside the integration is cosine squared theta d theta, which is an elementary integration, and the limits from negative pi over 2 to pi over 2. And you can prove that the answer of the whole thing will simply be pi and a square. So that's the area of the circle, which is what we expected from the beginning, because that's just a circle of radius a. So the area is pi times the radius squared. Now we calculated this using double integration and using polar coordinates. I hope it's clear how to go through the steps to calculate area. If you have any questions, please drop them in the comments. I'm going to continue and do more things, more maybe physical quantities to calculate. For example, if I think about this circle as a piece or a sheet of metal, for example, I would be interested in calculating the mass of the disk enclosed by that circle. I could be interested in finding the location of the center of mass. Or maybe if it rotates about one of the axes, so I would be interested in the moment of inertia around one of the axes. All these I could calculate using double integration and polar coordinates. I'm going to do them in another video, and I'm going to leave you now with this, and we will see you again in the new video to continue solving more quantities. Thank you.